My name is Curtis Johnson. I am part of the group of Brady Perrier, Joshua Perkins, and Girguis, and I'm presenting our results for the practice experiment we conducted last week. So, introduction and goals of the experiment. So the whole purpose was to record the transient response of a thermocouple, specifically a 1/8" type K thermocouple, when it was exposed to either boiling water or an ice bath, specifically an ice bath in our case. And by using heat transfer theory, the time constant of the transient response of the thermocoupler could be determined from plots of log normalized temperature versus time. All right, some important concepts to know going into the experiment. So if one assumes that the thermal system has no internal thermal gradients, essentially you're looking at the system as a black box of no serious complexity. You're essentially looking at it from the outside. You can treat it as a lump capacitance, which is something we did similar in our circuits class. And using that equation right there and integrating it over time, using the normalized temperature on the left, you can see that you can eventually spit out a result for the time response of the system. And we define the time constant as tau, and it has that value there, until finally, using that integration, you arrive at a value for time. And looking at the value for time constant, you can see by manipulating various physical parameters of the system, like the density of the fluid, the volume of the fluid, or even the enthalpy constant, you can actually change the time constant. All right, so the apparatus we used for the experiment was a 500 milliliter flask. It was half full of ice water. We used a type K thermocouple. It was a stainless steel sheet, of course paper towels, and a computation system with PDAQ data acquisition. All right, some pictures of our apparatus and setup. On the left, that's just the ice bath. And on the right, this is what our thermocouple looked like when it was submerged in the ice bath. During submersion, it was important to remember that we cannot press the thermocouple against the glass surface, because that could lead to some discrepancies in our temperature reading. And here's the fully assembled setup. And finally, close-up shot of the thermocouple device, the PDAQ data reading device. So here are our results. This is raw temperature versus time for insertion. So you can see it's an exponential decay in time. And then finally, here is our removal time versus temperature. Again, this is raw temperature. This is not normalized temperature. So this is actually pure temperature readings as they were coming out of the PDAQ system. All right, so here is the removal time versus the log temperature. And you can see that if you use a line best fit, you can pull a value for the slope of the chart. And by taking the inverse of that, you have the time constant response for the system. And when you take the inverse of the slope that we got here, this is for removal, you get about 250 seconds, which seems to be a little bit on the higher end. Okay, so just discussing our results, we achieved these results for the time constant value by taking the log of that normalized temperature difference. And again, once we plot it in time and examine the slope of the best fit curve line, simply taking the inverse will yield the time constant result. Some possible sources of error during the experiment. It was noticed that during the experiment, the connection of the thermocouple was a little faulty. It was leading to readings jumping up and down a little bit. So having a more effective thermocouple would definitely enhance the accuracy of our results. Also, during handling the thermocouple, there could have been accidental contact with the bottom of the beaker. And finally, the PDAQ system was not correctly logging time intervals with our temperature, so we had to kind of work in reverse from that. That might have had the effect of skewing our graph slightly to the left or slightly to the right, but ultimately would not affect our results for the slope of the graph. And some other important results not included here would be the log normalized temperature versus time for the thermocouple insertion. This would yield another thermal time constant for insertion that would be different for removal. And the reason for that difference in time constants between removal and insertion is because of the difference in the normalized temperature difference. You're essentially taking the difference between the actual temperature of the substance and the ambient temperatures. And during removal, that is far different than during insertion. The temperature gradient is much greater. Okay, and that'll do. Does anybody have any questions?
If there was a better connection to the thermocouple, do you believe that it would decrease the time constant?
If there's a better connection to the thermocouple?
Yeah.
Yes, because the time constant is essentially the measure of the thermocouple's ability to handle that transient response and see how quickly that's happening. So if the connection was better, it would definitely have a better response, a faster response.
But